So this is the ANOVA, sorry, this is the regression, and we are going to load the Brukutu data set. Now, in case you have forgotten, I'm going to just quickly show you. I normally don't do this, but I'm going to just quickly show you the Brukutu data set. This is something you've already loaded. If you haven't, or you have, we are going to check whether it's already loaded. So I'm going to show you mine. Okay, I'm going to show you mine so that at least you can appreciate yours. So look at this Excel. This Excel on your screen is exhibiting the Brukutu data set. Quantity demanded of gym bitters depends on price of the product, the complement price of the product, the income of the people, the location of the shop, the occupation of the people, and the religion of the people. So this data set, control, copy, and then take it to R, and then you load it. How to do it, I've shown you many times. Okay, so let's go back to our R. When you get to the R, we normally use this command to load the data. We normally use this command to load the data. And this is a command we normally use. There's a command. Okay. We use this command to normally load the data. The command here. Gene read.delay. Okay. So you already have it. If you have the data, to be sure that the data is loaded, just double click slightly the gene, G-I-N, and then run it. Just run mine. You can click here to run or do Control Enter to run. And then come down to the console. You see it's showing down here in the console. It's already in the memory. Ah, there you go. It's already in the memory. Okay. So you do that to load the data. All right. Now we are going to do our analysis. We are going to do our analysis. And most of you were typing the regression. So we are going to run the regression again. This is a command we are going to use to run the regression. But before we run the regression, we have to install and load the library data called jtools. jtools. Now, how do you do that? We've already shown you how to do that. Normally, you come to packages, and the packages you type install, and then after install, you type jtools. In fact, the moment you start typing, if your internet is really sharp, it will start showing, like mine is showing, jtools. I have already installed it, so I'm not going to click below install. Okay, and then you click below install, and then it will be able to install it very nicely for you. Okay, but I have done it already, so I'm not going to click below install. All right. So at this stage, I'm going to type this command. Okay, this command. I'm going to type it. Please, I hope you see it zoomed. Okay, I'm going to type run this command. Okay. Run this command in here. Gene multi, this is a command we are going to run. Okay, with kill PC blah 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 oku data and then summary. Now the way we are going to do this thing is different, and that is why we should load the library jtools. So to load the library jtools, just run it. Okay. And when you run it and you come down here, you see it written blue, which means that the jtools has been beautifully loaded. Now I want you to pay attention with me. Now I'm going to run the command. This is a new way of running a regression. It's beautiful. It's beautiful. You watch me. And so I'll use this command and then I'll summarize the result. I call the command gene multi. I summarize the result as gene multi with a sum, S-U-M-M. This is a new way of summarizing the result using the jtools. And once you do that, oops, let me do it again. Okay. Once you do that, you get this beautiful results. Look at the results there. This is a beautiful result. If it's not beautiful for you, it's beautiful for me. Okay. And this results will tell you the number of observations, which is what you see here, 40. The dependent variable, it will tell you kill. The type of regression, it will tell you linear regression. In fact, we are going to do other regressions for you to appreciate it. The fitness of the model, we normally use the R squared to determine the fitness of the model. Okay, this is 99%. And this have all been explained in the note. This means that 99% of the variability in the dependent variable Q, quantity demanded of gene bitters, 99% of the variability in that quantity demanded of gene bitters has been explained by the entire regression. Okay, only 1% hasn't been fully explained by the entire regression. So that's really, 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 really good. Okay, And then, of course, you have the estimate. You remember I told you that the estimate divided by the standard error will always give you the t statistic or the t value. And then, of course, it will also give you the p value. So this is where you are able to now interpret your results. But we'll come to the interpretation later. But for now, I just want you to know how this command is able to give you your OLS result. Keep this result in your mind. We'll combine other results and then we'll make some sense of them. The next thing is that you can use the command 115 to get your confidence intervals correct to 2 decimal places. Okay, so confidence interval, that is what some people like to use. So let's run that command and then we are able to see the confidence intervals. Okay, correct to 2 decimal places. So you can see from here that we have been able to remove the standard error, but now you have the 95% confidence interval plus or minus 2.5 and 97.5. This is a confidence interval. So what this means is that the negative 6.35 up to 0.04, that is the interval for the negative 3.15 price. Of course, you can still see that price has a negative relationship with the quantity demanded. In fact, in the previous videos, if you check, you will see that where we used only the price, it was significant. It was 14% negative, okay? And it was highly, highly significant. Now here, check the p-value. We are going to determine the p-value to see whether it's significant. And you can see from here that it is not that significant at 1%, okay? So we'll come to the interpretation. But for now, this gives you the confidence interval, the results with the confidence interval. Okay, the next one. And this result with confidence interval is good. I'll tell you why it's good. It's good because it helps you to know whether the thing is significant or is not significant. That's it. It helps you. It really does. I'll give you an example. Take an example like religion Muslim here. Religion Muslim here. Okay. Look at the coefficient of religion Muslim. What is the coefficient? Negative 23.01. Negative 23.01. Okay, that is a religion Muslim. Negative 23.01. Now, this is interesting. I like that. Negative 23.01. Let me just go down and show you guys something. This negative 23.01, if you look at it carefully, you will see that it is falling between the confidence interval. Okay, it is falling between the confidence interval. And that is why the p-value is 0, which means that it's significant. Now, anytime your estimate is captured in between the confidence interval, it means it is significant. Look at religion Christians. Okay, 15.55. It is within the confidence interval. So it tells you that religion is what? Is significant. That is why the p-value is also 0. But look at price. Look at price. Okay. The value of price is in principle within the confidence interval. Okay, it is within the confidence interval. But if you look at the upper bar value, okay, the gap is not wide. The confidence interval is not wider. And so that is why you can see that it was almost getting to be insignificant at the 5% level. And we'll explain that later on. Anyway, let's move on. Let's move on. We are going to now generate the plot. We did this in the simple regression. We're going to generate the plot for the entire regression, the predicted values and all of that. And to do that, you do this command. This command called effect. And that will give you this plot here. Okay, that you are seeing here. Let me just show you. That should give you the plot that you have here. And this plot is a clear, residual plot that you can have, a predicted plot that you can have. The line here is where everything is supposed to be, but then the scatter plots are not that much closer to the line. Okay, we'll talk about this when we get to homoscedasticity. But for now, let's look at the next command. Now, you can run the regression. Look at the regression that I did here. The regression that I did here, I included the, what do you call it? I included the constant, the intercept. Okay, you can see that I've included an intercept here. Okay, I've included it. But you can run the regression without including the constant. You can do that. You can do that. Okay, so the question becomes, how do you run the regression without including the constant? Well, that's the next command at the top there. Okay, let me try and see if I can zoom this. No. Okay, so if you look here, you'll see that command. Okay, so I've now given it a new name, gin multi underscore, okay, int, and you can see lmq 0. So the moment you bring 0 in front of it, it means you don't want the constant to be available. So watch it here. In this one, the constant is there. In the second one, there is not going to be any constant. So just watch. So you can see that the first variable that rather came is what? Is it? Now, why don't we normally need a constant? Well, many a time, sometimes you wouldn't even need a constant because it has no economic meaning per se. But this is just a model to let you know how you can suppress the constant. Then there is another one you can use to report robust standard errors. Okay, especially when we get to solving homoscedasticity, solving heteroscedasticity, okay, to homogenize the errors. And this command is one command you can use to generate homoscedastic standard errors. Of course, what I'm saying might not be fully understandable, but don't worry, when we get there, you get it. Okay, homoscedastic standard errors. And I decided to run this because I want to show you something beautiful about the tables. Because in most regression, authors would like to get nice tables to show. So that is it. You run it. After running it, you highlight just the name of the model you run. I call it gin multi robust, and just run it. Now, when you do that, look at the results. Look at the results here. And you will see that in the results, you will see the observation, but look at it. You still have OLS linear regression. But look at the standard errors. He's put there robust. And he's told you the type of standard error. Okay. This heteroscedastic standard error, there are several of them. Okay. HC1, HC0, all the way up to HC5. I've explained all of this in the note. Okay. And this is per the recommendation the author will use. If you use Stata software, they use the HC1. Okay. But you can use any recommendation. We can change everything. And if you look at that, you can see that now the price is what? Significant at 5% easily. At first, the p-value was 0.05, but now it is 0.04. Okay. If I should change the HC1, where is that? If I should change the AC1 and I make it HC3, I will get a different result. And that HC3 will be a different kind of regression. Where is that? You come and just run it here, and then you get this. Okay. You see that one, the p-value for the price has changed to 0.06. So it's no longer significant at 5%. So again, the ones that you use are very important. The kind of HCs that you use are important. And we'll look at the details of all of this at the right time. Now, ladies and gentlemen, now that you are done with this, you want to show your results and compare. I want to do one quick regression. I will later talk about this regression and then use a table to show you how you see it in journal articles. And this is a GLM, the generalized least model. Okay. I just want to run the same thing by putting this command here called GLM. A generalized model, and then we can run the results and see. This is a generalized least model. You can see it here written here. It didn't write OLS regression. It rather wrote linear regression. Okay. It calculated the pseudo R square, the Akaike information, the BIC, and several other things. Okay. This is a maximum likelihood estimation. Again, we'll come deeply into this to appreciate. Okay. But the most important thing is this. Now you have run several models. Okay, how do you deal with it? You install a command called hackzable. Hackzable. This is a command. Hackzable. So you will now go to your package section. You will click on the package. You will type Hugs. Sorry, did I say Hugs? Hugs table. Hugs table. Hugs table. The moment you even start typing Hugs, the table will show. Okay. I don't know whether yours show, but yeah, I think it shows. The table will show. Then you can install it. And then once you've installed it, you can commandeer it into the library. So this command will bring it out into the library. And then all your commands, your models you've indicated, you will export them in this beautiful table. Now, this is what I wanted to watch. Okay. The first one was our OLS command. We called it gene multi. The second one, we called it gene mock underscore int. The next one, we called it gene multi robust. Okay, that is the name we gave to it, gene multi robust. And then we have gene multi GLM. Okay, and then we can add this scale as true. Now let me export this and then watch what happens. This is the final result. Now the final result is a beautiful final result. Let me just raise the whole thing. And you can see that now it has organized everything into model 1, model 2, model 3, model 4. And you have all of the models, each one with a standard error. And then the stars will be telling you whether it's significant at 1%, 2%, or 3%, or 1%, 5%, or 10%, okay, or even 0.01%. And this is what you will normally see in journal articles, okay, where they have combined everything. So you don't have to go and arrange everything in Excel. Okay, you can let R do everything nicely for you. And at the bottom, you still know the observations, those that have the R square values. Okay, some of them, the R square values are 1. Look at model 2. Okay, model 2. If you go and check carefully, okay, the model 2 is being represented by, when you check it, it is the one with gene more underscore int. Okay, and that very model was the one that we did, which was it will remove the intercept. Okay, so that was the one that removed the intercept. So when the intercept was removed, you can see that the R square is 100%. And then you have other information which we shall look at later on. Ladies and gentlemen, your ability to be able to generate these kinds of results are very important, especially when you are doing model cross-checking. It's very important. Sometimes you'll be doing fixed effect model, random effect model, systems GMM, truncated bootstrap regression, two-stage least square regression, and things like that. You can now beautifully let R organize it into a table like this using Hacks table and then doing the necessary commands in that regard. Okay, so at this stage, I will wait for questions. Anybody who will have any questions?